Hello, music nerds! Today, we're looking at Chapter 3 of Hermann Helmholtz on the sensations of tone. The link to the webbook that I'm reading from is in the description. You can find the entire text of the book there as well as all the apps that I'm going to show you in this video, so let's get to it. Chapter 3, Analysis of Musical Tones by Sympathetic Resonance. At the end of Chapter 2, if you remember, we were left with the question of whether there was any practical use of analyzing composite vibrations into simple vibrations apart from the theoretical. And at the beginning of Chapter 3, Helmholtz says, yes. We proceed to show that the simple partial tones contained in a composite mass of musical tones produce peculiar mechanical effects in nature altogether independent of the human ear and its sensations, and also altogether independent of merely theoretical considerations. These effects consequently give a peculiar objective significance to this peculiar... He sure likes the word peculiar, doesn't he? A peculiar objective significance to this peculiar method of analyzing vibrational forms. Such an effect occurs in the phenomenon of sympathetic resonance. Sympathetic oscillations, or sympathetic resonance, is the reason that a small boy can ring a church bell much heavier than himself. By pulling on the rope in the correct periodic intervals, he can add his force to the oscillation of the bell, so that it moves further and further every time he pulls, and eventually start ringing. Helmholtz suggests this simple pendulum for those of us who don't have access to a belfry, a piece of string with a ring tied to the bottom of it. As the ring down at the bottom oscillates back and forth, the movements of your hand at the top will affect the oscillation of the ring at the bottom. Now we have it even easier. You don't even have to tie a ring to the bottom of a string. We have an app to do it for us. The movement starts very small, but we can move the top slightly in opposition to the movement at the bottom, and that should increase the movement of the pendulum. Let's see if we can get it to go all the way around. Yeah! The great thing about the app is we don't have to deal with friction. Now, of course, you don't have to move your hand at the top every single time the ring swings in order to make the ring swing further. You could move it every 2 or 3 or 4 swings. Now let's look at the movement of your hand at the top of the pendulum as its own periodic vibration. Analyze the periodic motion of the hand into a sum of simple pendular vibrations of the hand, exactly in the same ways we laid down in the last chapter for the periodic motions of the particles of air. Then, if the periodic time of one of these vibrations is equal to the periodic time of the pendulum's own oscillations, the pendulum will be set into violent motion, but not otherwise. Let's try and set this pendulum into violent motion. The frequency of the motion at the top starts at 1.5 that of the bottom. Let's bring it down. To unison. That should set us into violent motion. There we go. The same principle holds true for vibrations of much shorter frequencies, like the vibration of the string of a pianoforte. Gently touch one of the keys of a pianoforte without striking the string so as to raise the damper, and then sing a note of the corresponding pitch, forcibly directing the voice against the strings of the instrument. On ceasing to sing, the note will be echoed back from the piano. Or put a piece of paper on top of the string and watch the paper be jerked off when it's set into sympathetic vibration. And of course, you don't need to use your voice, you can use any other instrument. Let's try it. We have our virtual pianoforte string here with a resonant frequency of 110. And these gray marks above the piano here show us which notes should set the string into sympathetic vibration. Let's change the resonant frequency. And let's try and sing it into sympathetic vibration. Ah, ee, ooh. I feel like I'm trying to break a glass or something. Ah, ooh. There we go. Still, it is well known that bell-shaped glasses can be put into violent motion by singing their proper tone into them. Indeed, it is related that singers with very powerful and pure voices have sometimes been able to crack them by the agitation thus caused. The principal difficulty in this experiment is in hitting the pitch with sufficient precision and retaining the tone at that exact pitch for a sufficient length of time. Don't I know it? So he moves on to look at sympathetic resonance in elastic membranes. Let's take a look at this membrane with a resonant frequency of 132. Something you might have noticed about these notes with the gray lines is that they are not harmonic like they were with the string. These notes, which set the elastic membrane into sympathetic resonance, are called proper tones. It is only exceptionally, as in strings and the narrower kinds of organ pipes, that these proper tones correspond in pitch with the harmonic upper partial tones of a musical tone. They are, for the most part, inharmonic in relation to the prime tone. In figure 15, he shows us this contraption with an elastic membrane over the bottom of a bottle with a piece of silk thread attached at the top here that has a little piece of wax dangling on it. And whenever this membrane is set into sympathetic resonance, the piece of wax goes flying. So it becomes very visually obvious when the membrane is in sympathetic resonance. And with an experiment like that, the pendular vibrations into which the composite motion of the air can be analyzed here show themselves capable of producing mechanical effects in external nature independent of the ear and independently from mathematical theory. Hence, the statement is confirmed that the theoretical view which first led mathematicians to this method of analyzing compound vibrations is founded in the nature of the thing itself. And then we get to the famous Helmholtz resonators. Here's a figure of one, and here's a figure of another one. He's essentially taking this design and replacing this elastic membrane with your eardrum. If we stop one ear and apply a resonator to the other, with this B end here, most of the tones produced in the surrounding air will be considerably dampened, but if the proper tone of the resonator is sounded, it brays into the ear most powerfully. A properly tuned series of such resonators is therefore an important instrument for experiments in which individual faint tones have to be distinctly heard, although accompanied by others which are strong, as in observations on the combinational and upper partial tones, and a series of other phenomena to be hereafter described relating to chords. So at the end of the chapter, he promises to use these resonators in experiments to be described in future chapters. If there was anything in Chapter 3 that you want to read more thoroughly, or if you want to try and set that string into sympathetic vibration using the dulcet tones of your beautiful voice, go to sensationsoftone.com, and I'll see you back here next week for Chapter 4. Bye.